We're going to start our new topic today on variation. So we're particularly looking at direct variation to begin with, which is just a fancy way of saying that one thing directly relates to another. So these two different equations, these are called direct variation. And this is the little symbol we use. So this means that y is directly proportional to x. All right, so this is an important symbol that you're going to see a lot. So this is the nice little equation we like to use. So k can just be any number really. So we're just going to use k. I honestly don't know why we use that letter, but we do. And it means the constant of proportionality. So anytime you're asked to find the constant of proportionality, you're being asked to find whatever this number is here in front of x. All right, so for example, you can have these things as well. So these are also direct variation, even though now we have powers attached to them. And it just depends how we write the equation as to whether or not that's true. So here I said y is directly proportional to x. So this statement does not apply to these situations over here, because what I actually need to do is say that y is directly proportional to x squared if I want that to be true. I could say y is directly proportional to x cubed over here. Right, so what I can do is actually say certain things. But what I can be doing is say y is proportional to x to the power of k, right? I can put something up there, but there can also be a k in front, so you know what I mean. So this number can change and this number can change, but we've got various things going on, and it's just a matter of how we write that. So if we were to plot this on a linear graph, we could. So I'm just looking at the top half here. So this relates to this. So these equations are going to look like this, right? It's a straight linear graph. We should know by now that linear graphs don't have any powers greater than 1 attached to the variable. So x never has a power greater than 1. But here, see how I've written, even though x squared, so hopefully we know that x squared is actually a curvy graph. But if I plotted this differently, if I called this x squared and this y, then I could turn it into a linear graph. You're not actually going to be asked to do that right now. It's just good to be aware of that. So if I change my scale, I could make a linear graph out of this equation, as long as this has a different scale to this. So this is just y, but this would be x squared. And that's just showing that they're directly proportional. Okay, another one is inverse variation. So this time we're going to have a fraction going on. So I could say that y is directly proportional to 1 over x. So then this is our nice little formula that we're going to use for that one, where k is the number on top of the fraction, whereas before it was the number in front of x. Now it's on top of a fraction. So let's practice finding some of these. So the important statement is always at the start. So we need to pay attention to what we're told here. Sometimes it'll be written like this, sometimes it will be written in a sentence. Y is directly proportional to x. So this is really important. So something like this is going to be different and I will treat it differently. But for now, I just need to know that y is directly proportional to x. So I know that y equals kx. Okay, so that's my lovely equation I'm going to use. Now I'm going to plug in these values. So when y is 12, x is 4. So now I've got enough information to discover what k is. Well, if there's no sign, these two things are multiplying each other, so I'm going to undo that by dividing, which means k equals 3, which means I need to put it back into this form, so y equals 3x. That is my final answer. And you could test it to see if that was true. So 12 equals 3 times 4. It does. Fantastic. So you can check it with your original values and make sure you got it right. All right, same thing here. I said that y is still proportional to x, so y is equal to kx. So when y is 4, x is 12. So I've actually gone backwards this time, haven't I? I've got the same values, but they're backwards. So then 4 over 12 is k, which means k is 1/3, right? I'm going to simplify my fraction. So that means y equals 1/3 k. That is my, x. That is my final equation. And again, you can check it. 12 equals 1/3, 4 equals 1/3 of 12. Yes, it does. Fantastic. All right, so this is exactly the same, but this time I have a squared going on. So I need to take that into account when I'm doing my original equation. So y equals kx squared this time. So Then I'm going to put in my values like I did before. So 12 equals k times 2 squared. So that means 12 equals k times 4. So 12 divided by 4 equals k. So then k is 3. So then I go back to my original equation and say y equals 3k. Why do I keep doing that? Y equals 3x squared. And again, I could check that to see if it's true. So y is 12. 12 equals 3 times 2 squared. 2 squared is 4. 3 times 4 is 12. Great, it works. All right, let's look at one more. This time I'm being told that y is directly proportionate to the inverse, so it's 1 over x. So 1 equals k over x is what I'm being told is my equation I'm going to use this time. And then I'm going to plug in my values. So if y is 5, I don't know what k is, and x is 3. So then what I'm going to do is move this around. So if this is dividing, I'm going to bring it across. So I get 15 equals k. So then that means y equals 15 over x. And that is my formula. And again, I can check to see if that's true. So y is 5, so 5 equals 15 divided by 3. Yes, it does. Fantastic. There is my answer. All right, so we're just going to practice using proportionality today. Remember, k is called the constant of proportionality, and you're going to be using direct variation and inverse variation. Let me know if you have any questions.